Hi, this is problem 17 from the AMC 12A. 8 people are sitting around a circular table, each holding a fair coin. All 8 people flip their coins, and those who flip heads will stand, while those who flip tails will remain seated. What is the probability that no two adjacent people will stand? So let's draw our table with 8 seating locations. And it looks like we're flipping a coin at each of these locations, and what we're really asking is, what's the probability that if we flip a coin at each of these positions, what's the chance that no two heads will be adjacent to one another? That's kind of the essence of the question. So let's try to answer this using the basic ratio definition of a probability as being the number of event outcomes that satisfy that condition divided by the number of all possible outcomes. And the denominator looks a little easier to tackle. Let's do this one first. So it looks like we have a coin toss at each of 8 locations. The coin can come up heads or tails, and these are independent events for the different locations. So we can use the multiplication principle to compute the total number of head-tail patterns around this table as just being 2 times 2 times 2 all the way around 2 to the 8th, which equals 256. And that looks pretty encouraging. That shows up in some of our answers. So it looks like we're on the right track here. So let's now try to calculate the numerator here, the number of event outcomes that satisfy the condition that the two heads are never adjacent to one another. So that seems kind of complicated how that may occur, and I don't really see a way to do that in one pass. So we're going to have to do this in cases. And so let's try to organize this in terms of cases based on the number of heads that are showing up. And so in the simplest case, we can have like the case of no heads, so they're all tails. And there's only one way that that can happen. You'd have to have a tail at each location. And the only way that can happen is one way. So let's tabulate the number of ways for that being 1. If we had one head showing, that one head could appear at any one of the 8 locations. So there are 8 ways for that to occur. If we have 2 heads showing, then it appears as though we could choose the first head to be any one of the 8 locations, and having chosen that location, say 8, there would be 5 remaining locations for the other head to appear so as not to be adjacent to the first head. So that works out to 8 times 5 ways using the multiplication principle. But we're doing a double count here that's a little bit subtle, in that when we try to count it this way, we realize that we would count the 8 and then the 6 as a pair, but when we get around to choosing the 6, we would also count the 8. So we're basically double counting by the number of permutations of the 2 objects. So we have to divide this by 2 factorial to give us the total number of ways that are distinct head-tail patterns as being 20. Now when we get to 3, this is where things get a bit complicated. Here again, we can choose our first head to be any one of the 8 locations. Now having chosen, say, the location 8, the total number of remaining locations for the other 2 heads would have to be somewhere between 2, 3, 4, and 5, and 6. So that's 5 remaining locations to place the 2 other heads. But now these 2 other heads cannot be adjacent. And that turns out to be a familiar problem pattern where, for instance, we had 5 chairs and we wanted to seat 2 people in the 5 chairs, but we don't want them to sit next to one another. And that permutation turns out to be 3 times 4. But here again, now we have 3 objects that we're overcounting by a multiple of 3 factorial, so we need to divide that by 3 factorial, and that gives us a final count of 16. Now this case is pretty complicated, and we'll talk about this case in another way in a minute, but let's continue with this as we go. If we had 4 heads showing, that's a pretty simple case, because with 4 heads showing, the only way you could separate them each by some spacer is to have the four heads at either the odd seat locations or the even seat locations. So that's essentially two patterns for four heads showing. And if we get to five heads, we find that there's really no way to place the five heads so that no two heads are adjacent to one another. So this is 0, and for 5 and greater, it's still 0. So here we can count up the number of ways as being 2 plus 8, that's 10, 16, 26, 27, 47 total ways. And that gives us the probability of 47 over 256 for choice A. Now let's take a look at this case 3 a little bit more from a different angle. This is a bit of a difficult computation, and another way to figure out the total number of ways is to take a look at the patterns for what could appear for the three heads. So let's take a look at our 8 locations and look at one pattern where two of the heads are opposite one another. And that only leaves one of two possibilities for the other head. It'll have to be in a position to form sort of a right triangle with the other two heads. And there are 8 ways to spin this right triangle around to create all the equivalent patterns of three heads following this right triangle principle. So the total number of ways is given by 8. Let's consider another pattern where we have our 8 locations and we choose one at the top, and we choose the other 2 locations to form sort of a isosceles triangle around the table. And here again, we can take this pattern and spin it around to the 8 different locations to create 8 additional ways to arrange the three heads. Now it turns out that we've exhausted all the patterns with these 2 basic patterns, and we notice that if we were to take this vertex and move it over by 1, we would basically create another isosceles triangle that would be identical to the first one, and it's just oriented over by a few locations. So this is essentially the same pattern as the previous isosceles triangle, and this really doesn't generate any new patterns. So it turns out that these 2 sets of patterns exhaust all the possible ways that you can arrange the three heads around the 8 locations across the table, and that works out to a total of 16, which matches our original count. So that's just a second way to do this count for the more difficult case of the three heads showing. So anyway, that's a pretty tough problem, but again, it kind of works out to the basic ratio definition of probability as being one of the key ways to solve these types of AMC probability questions. So hope that was clear. Take care.